Okay, so yesterday we looked at operations on functions. We talked about how you can add, subtract, multiply, and divide. And today, what we're going to look at is compositions of functions. Now, if you want to think of what a composition of functions is, to compose two functions. If you think about like a musical composer, what they do, they write music, they take different instruments, they put their sounds together to make one really beautiful like symphony that all is one thing. And the idea here is similar. We're composing two functions together. We're going to take one function and blend it with the other one, basically, is what's going to happen. Okay, so if I have a function g and I want to do a composition of g with a function f, then if we call that new function h of x, then it would look like this. So h of x is equal to, you would read this as g of f of x. Okay, so f of x is the inside, and then whatever f of x is, we want to do g of that. And if you look at this picture over here to the side, it is a good kind of illustration. So we start with x, and that's what we plug into f. So what we get out then is f of x. Well, f of x was the output for f, but now we're going to make f of x the input for g. And so the result is the output of g. And if you think back to like Algebra 1, you talked about sort of the idea of these function machines. Okay, so if we think about this, I have this little machine right here, and this function is f. Okay, so if I start with x and I throw x into my machine, I do whatever f is to it, and out comes f of x. Well, then what we do with a composition is now we're going to, rather than put something new in, we are going to take this exact f of x, and we're going to call this one g, and we're going to plug f of x into g, and so what we get out is g of f of x, because that's what we plugged into it. So the basic idea of this is really not anything new. So what we're doing is we're going to take one function and use it as the input for a different function. Remember when we did function transformations and we said a horizontal translation is f of x minus 2. So we took x minus 2 and replaced that where the x's are. It is the exact same thing. And just a side note here, sometimes you'll see this alternative notation right here, which also would be read as f of g of x. Whoops. Okay. This little tiny circle, it's not a 0 or an O or anything like that, it's just a little circle, that represents the composition. So that basically says f composed with g of x. This one here is more similar to the notation we saw yesterday, like f plus g of x, or, you know, something like that. So here it's kind of using composition as another operator, but it means the exact same thing as what we wrote before, f of g of x. Okay, so it is always best to work from the inside out. Okay, so we start and we're going to do f of g of x. So g of x was what goes in the inside, and by the functions that we're given, g of x is equal to 5x plus 1. So that means that I want to do f of 5x plus 1. And to do that, remember what we do is we're going to take the x out of f of x and replace it with our new input, which is now 5x plus 1. So we have 3 times whatever we plug in minus 2. Well, what we're going to plug in is this input right here, 5x plus 1. And so now we just want to simplify by distributing, combining like terms, anything we can do there. So to start, I'm going to do 3 times 5x, that's 15x. 3 times 1 is 3, and then I have minus 2. These make like terms. So 15x plus 1 is what we get for f of g of x. Now, we can do this in the opposite direction as well. If I want to do g of f of x, if we look at example 2, now I'm going to put f of x here. And so that means that we want g of f, which is 3x minus 2. So since g is 5 times an input plus 1, the input that we're going to use is 3x minus 2 because this was f. Okay? So again, this time we get 15x minus 10 plus 1, so we get 15x minus 9 this time. So you see it was similar, but we did not get the exact same thing when we plugged those in. Okay. If we look at number 3, this one always seems a little bit weird. We want f of x. What that is saying is take f of x and plug it back into itself, basically. So, in a similar fashion, we know that f of x is equal to 3x minus 2, so that's what we're going to start with. So, that means that I want f of 3x minus 2. And since f is 3 times some stuff minus 2, then we just end up plugging the same value back in there. And so it seems kind of bizarre, but that is possible. We can do that. And so when we distribute, we get 9x minus 6 minus 2, which makes 9x minus 8. Now, the last thing is you'll notice on number 4, this one is a little bit different because we're not doing f of g of x, we're doing f of g of a value. So this time we want f of g of 3. And we could do this one of 2 ways. We could take what we got for number 1, because that's f of g of x, and we could just plug 3 into that. But let's say that we didn't know what f of g of x comes out to be. Well, like I mentioned before, we just work from the inside out. So in this case, we would start by doing g of 3. And g of 3 means take g and plug in 3 for x. So this would be 5 times 3 plus 1, which is 16. And now we want to do f of 16. We take the output of g and make it the input of f. And f says do 3 times your input minus 2. So this comes out to 46. And that is the answer. F of g of 3 is 46. And so you should get the same thing if you plug that into the answer we got for number 1. Let's look at just a couple more examples here. For 5, 6, 7, and 8, I'm not going to do every single one here, but I just want to point out you have to be real careful with the squareds, okay? F of g of x is a pretty simple one. So I would like for you to do this one. That will need to be completed when you come in tomorrow. And then for number 6, g of f of x is where it gets a little bit trickier. So f of x in this case is x minus 4. Whoops, I don't want f, we're doing g. So we want g of x minus 4 because that's what f of x was equal to. So when I do that, g of x is 2 times x minus 4 squared minus 3 times x minus 4. So this is what we substituted in. Those are where the x's used to be. Okay? Now, you have to be real super careful when you square a binomial. Remember the rule that I told you is that if I have a plus b squared, we're going to square the first, square the last, and it's always positive, and then we're going to multiply a times b and double it. And these two signs, here and here, are always going to match. Now, you can do that little trick, square the first, square the last, multiply and double, or you can just plug into that formula. It does not matter how you do it. But here's what's very important. Exponents come before multiplication, so you cannot distribute that 2 until we have squared it. So we get 2 times, square the first, that's x squared, square the last, we get plus 16. X times negative 4 is negative 4x, times 2 is negative 8x. So that's what we get when we do x minus 4 times itself. Okay, and then we can go ahead and distribute this 3, so I get minus 3x plus 12. But now here we have to distribute this 2 to all three things. So we get 2x squared minus 16x plus 32 minus 3x plus 12. And we want to go ahead and combine our like terms. So these can go together and these can go together. So our final result is 2x squared minus 19x plus 44. So you can see when we get up to exponents, it can get kind of messy, okay? But that's okay. It doesn't necessarily make it harder. It just gives it more steps. And so 7 and 8 are going to be more examples of where we're going to evaluate one at a time. So, for example, on number 7, there should be another parentheses right here, I'm noticing. So we want f of g of negative 1. So that means we work from the inside out. We're going to start with g of negative 1, which means I want 2 times negative 1 squared minus 3 times negative 1. Well, that's 2 times 1 plus 3, which is just going to be 5. And now we take the 5, and now we want f of 5. And f is easy. It's just x minus 4, so we just get 1. Okay? So I would like for you to do number 8 as well. You can check, I don't know if I have notes posted for this, but you can check the calendar to see if notes are posted so you can check your answers there. That is what we want to have. So you need to have all 4 of those examples, including 5 and 8, done when you come in tomorrow if you want to participate in the activity. Now I want to show you one more example here, okay? And number 9 is exactly the same as what we were just doing, so I'm going to leave that one for you guys to do. Number 10, you'll notice we've got 3 things. We want g of f of g of 2. It just means we have to do 3 substitutions instead of just 1. And again, we always start from the inside out. So that means we're going to start with the one that is closest to the 2. So first, I want g of 2. And g is 6 times your input plus 4. So that's going to come out to 12 plus 4, which is 16. Now, the next level, if we go, is f of that. So now we want f of 16. And f is 3 times 16 squared minus 5. So that's going to get real big. 3 times 256 minus 5, and I don't know what that's going to be, 600, 750, 768. That might be wrong. I don't have a calculator handy. I'm trying to estimate this really quickly. So that sounds right to me, though. So when we're all done there, we get 763. But again, we are not done because we still have one more time through g that we have to do. So the last one here is now we're going to do g of 763. And again, if that 763 is wrong, this is going to be wrong, but I'm relatively sure that that's good. So we have 6 times 763 plus 4. And that one I'm not even going to attempt to do in my head. 7, 3, 45. So we have 4,578 plus 4, which gives us a final answer of 4,582. So you're going to see a couple where you have to do maybe several, and we could pile on a gazillion of these. We could do g of f of g of f of f of g of f of g of x, or of 6, or whatever. We could do it as many times as we want, You just have to follow the directions. And so you're really working right to left in that case. You're starting from the innermost function and working out towards the layers until you get all the way to the outside, the outermost function. Okay? So that is what I have for you today. You should have all examples done, 1 through 10 for this composition section. Is that 10? Yeah, 1 through 10. When you come in tomorrow, you show me those. That's your ticket into the activity back in the flex space. And I will see you tomorrow.